Hey everybody, I'm going to take you through the answers to the Gas Law FRQ for Unit 6. Here's the first one. Part A is just a standard ideal gas law problem, except instead of having moles, you have grams of PCl5, so all we need to do is convert from grams to moles, insert it into Pivnert, and solve for P. If I take 6.19 grams of PCl5 and divide by its molar mass, I get 0.0297 moles of PCl5. Now I have everything I need to solve for pressure in ideal gas law. Rearrange Pivnert to solve for P, and I get nRT over V. Now I just plug in the numbers that I have. Number of moles is 0.0297. The ideal gas constant is 0.08206. Liters times atmospheres over moles times Kelvin. Temperature is 252 degrees Celsius, but don't forget to add 273, and you get 525 Kelvin. All that is over V. The volume of the flask is 2 liters. Plug all this into my calculator, and I get an answer of 0.640 atmospheres. And that's the answer for Part A. Now I'm going to scroll down a little bit and give myself some more room to answer Part B. Part 2 says that some of the PCl5 dissociates into PCl3 and Cl2, and the total pressure inside the container is 1 atmosphere. And so some of that's the PCl5, some of that's the PCl3, and some of that's the Cl2. So the first thing I'm going to do is use Pivnert to solve for n number of moles of total gas in the container. I have everything I need to solve for n, so I just plug it in and solve for n. The pressure is 1 atmosphere. The volume is still 2 liters. R is still 0.08206. Temperature remains 525 Kelvin. If I put this into my calculator, I get 0.0464 moles. Now that gas is going to be considered NT for total moles of gas. That number of moles is equal to the sum of the moles of all the gaseous species that are in the container, and that includes the PCl5, the Cl3, and the Cl2. Now we knew that we originally had 0.0297 moles of the PCl5 to begin. That was from Part A. So we're going to let X stand for the amount of gas lost by PCl5, but also equal to the amount of moles of gas gained by the PCl3 and the Cl2. Since everything's 1-to-1 ratio, the moles lost here is equal to moles gained here and here. Once I identify those variables, then I can take this information and plug it into this formula. So I write it out. I have 0.0464 moles is equal to 0.0297 moles minus X plus X plus X. And if I combine like terms and simplify, here's what I get. 0.0297 moles plus X, because the negative X here cancels out the positive X there, and all you're left with is 1 remaining X. All for X, I get 0.0167 moles for X. Number is equal to the moles of PCl3 and also the moles of Cl2. This doesn't actually answer my question quite yet, because I need to find the partial pressures of the PCl3 and the partial pressures of the PCl5, but now I have all the information to set up the handy-dandy moles to pressure direct relationship that we talked about in class. Everything I need except P1, and we're going to call P1 the pressure of PCl3. The overall pressure of the system is 1 atmosphere. The number of moles that we just calculated by calculating X up here, I plug that into N1, and then the total number of moles was something we calculated up here after we did the Pivnert. And so everything that we have except for PCl3. If I take 0.0167 moles divided by 0.0464 moles, I get 0.360. That's the pressure of the PCl3. Remember, originally the total pressure was 1 atmosphere. That's the sum of all the pressures, and we just calculated the 0.360 atmospheres of PCl3, which happens to be the same pressure of the PCl2, so I plug those in here and here and call PCl5X, and then I simply subtract those two from each side and find X is equal to 0.280 atmospheres. This is the pressure of the PCl5 after the reaction has finished. So there you go. I have my two answers, 0.360 atmospheres of PCl and 0.280 atmospheres of PCl5. You may have come up with an alternate way of doing this with less steps. As long as you show your work and I can easily follow your work, you'll get full credit on the quiz on Wednesday. Here's the answer for question number 2. After reading through the question, I find that there is a total pressure of 1,146 millimeters of mercury and a partial pressure of 24 millimeters of mercury, which is due to the liquid water in the container. So first thing I need to do is isolate the pressure of just the gas mixture. So I'm going to subtract 24 millimeters of mercury on each side to find X. We're going to spark this and combust H2 and O2 to make water. We need to write out a balanced chemical reaction to figure out which one's going to run out first. So you have 2 moles of H2 and 1 mole of O2 in this reaction. If you start with equal moles of each, as it says in the problem, this one's going to run out first because for every 1 mole of O2 you use up 2 moles of H2. So the H2 is going to run out first. And since you have equal molar of each, you also have equal pressure of each. So if I take this number right here and split it in half, half of the pressure is going to be attributed to the H2 and half of the pressure is going to be attributed to the O2. Simply because I enjoy working in atmospheres rather than millimeters of mercury, I'm going to take this 561 and convert it to atmospheres by dividing by 760. When you do that, you get 0.738 atmospheres of H2. Set up Pivnert. You got everything you need to solve for moles. If I rearrange Pivnert to solve for moles, you get N is equal to PV over RT. So 0.738 atmospheres times 0.5 liters divided by 0.08206 divided by 298 gives me an answer of 0.0151 moles of H2. Figure out how much O2 gets used up. We're going to do some quick stoichiometry here, but you'll take the 0.0151 moles of H2 and multiply by the mole ratio. And taking that number of moles and multiplying by 1 over 2, you get 0.00755 moles of O2 used. Since you started with equimolar H2 and O2, you subtract this number from this number, but this is moles of O2, and you get 0.00755 moles of O2 left over. I'm going to clear out a little bit more room so I can solve part B. Since all the H2 is used up at this point, the only thing left to contribute to the pressure is O2, whatever water was produced, which is now lying in the bottom of the container. There's 0.00755 moles of O2 left over. That's what's in the container multiplied by the R constant. This time multiplied by 363 Kelvin because they say the temperature now is 90 degrees Celsius. The container is still half a liter. The pressure of O2 is equal to 450 atmospheres. But remember, the pressure inside the container isn't just the pressure of the oxygen, but also need to account for the vapor pressure of the water inside the container. It's mentioned that it is 526 millimeters of mercury. Again, I'm going to change that to atmospheres so I can add these two units consistently. So I take that millimeters of mercury and divide by 760 to get 0.692 atmospheres. Now I take the 0.450 atmospheres of O2 and add that to the 0.692 atmospheres, which is the vapor pressure of the water, and I get a total pressure of 1.14 atmospheres, which is my answer for part B. So in part C, your job is to calculate the number of moles of H2O as vapor in the container, and we're going to use that pressure that we just calculated from part B, 0.692 atmospheres. The number of liters is still 0.5, R is still 0.08206, and the temperature is still 363, so all we need to do is set up a quick Pivnert and solve for N. I plug all my variables in, and I hit enter, I get 0.0166 moles of H2O. And that takes care of part C. Well, hopefully you're able to follow all my work. That takes care of this video lesson. Thanks for watching.